Now for acids and bases, the concentrations involved are usually small. And we get tired of writing times 10 to the negative 7, times 10 to the negative 9th, etc. And so the topic of section 16.4 is pH. And pH is a way to simplify the numbers that we're working with. And pH is defined as the negative log, and this is a base 10 log, it's not a natural log. And so unlike what we've been doing with the Arrhenius equation in the kinetics chapter and things, you're going to have to find your base 10 log button on your calculator. So that's the base 10 log of the H3O plus concentration. So if I have a H3O plus concentration that is equal to 1.00 times 10 to the negative 7th, that was the concentration for pure water. Well, if I put that into my formula here, then I get the pH equal to 7. And a pH of 7 is perfectly balanced between acids and bases. If I have an H3O plus concentration that is less than that, let's say, I'll just pick some numbers, 6.4 times 10 to the negative 11th. Well, let's figure out what that pH would be. Well, I'll write it here first. pH is equal to negative base 10 log of 6.4 times 10 to the negative 11th. And most of your calculators, it'll just say log, L-O-G, instead of the ln of the natural log. So that's how you can make sure you're hitting the right button. So let's figure out what this pH would be. I want to take the negative base 10 log of 6.4 times 10 to the negative 11th. And it looks like the pH is 10.19. Okay, and before we get too far here, let's address the question of sig figs. I, in fact, should have written 7. In this case, 000 for this answer to match the sig figs here. And with whenever you're doing logs, the sig fig rules get a little bit tricky. And so I'm not going to dwell on this too much, or I won't be taking points off for sig fig problems that involve pH unless they're flagrantly wrong, like you just put 20 sig figs. But here we've got 3 sig figs, right? And here we have 2 sig figs. And so our answers should have 3 sig figs and 2 sig figs. And here's the rule for pH. Only the numbers after the decimal count. So this has 3 sig figs, and this has 2 sig figs. The 7 and the 10 do not actually count as significant figures when you're taking the pH of something. So you're probably used to talking about pH of 7 as being neutral. I think that's something that most college students have been exposed to a little bit. And so pH scale, when you have larger pH values, then those are more basic. And I forget the numbers of what we just calculated, but it was something where the H3O plus concentration was lower than for pure water, and it had a pH of 10 point something, right? And so that was basic. And pH that is lower than 7 is acidic. And you probably have some vague notion that, like, the pH range goes from 0 to 14. There's a nice symmetry to that. But guess what? It's wrong. We can have acids with a pH of negative values. It can crash right past 0. And we can have bases with a pH above 14. There is nothing special about these numbers at all. 7 is special. That is the middle. And a pH of 0 just means you have an H3O plus concentration of 1 molar. Well, what if you have a concentration of 2 molar? Well, now we've entered the negative territory. And 14 means that you have an OH minus concentration of 1 molar. And a H3O plus concentration of 10 to the negative 14th molar. And again, you can crash beyond that number easily enough. You just need to have a particularly high concentration of your acid or your base. So again, your textbook shows how only the digits after the decimal point are significant. And here we can look at some common substances. Stomach acid has a pH in the range of 1 to 2. Believe it or not, soft drinks are just above that with a pH of 3. Orange juice and tomatoes are 3.5 to 4, and rainwater is 6. Pure water is neutral at 7. And you can get an idea. Oh, sorry. Let me back up just a minute here. In case it wasn't clear, by defining pH as a log base 10 scale, each unit on the pH scale represents a factor of 10 in the hydronium ion concentration. So the difference between 6 and 7 looks modest, but rainwater has 10 times the H3O plus concentration of pure water because that's 1 pH unit. What about rainwater versus tomatoes? Well, tomatoes have 100 times more H3O plus than rainwater, 1,000 times more than pure water. Does that make sense? It's all based on powers of 10. We can look at pOH. Human blood is actually slightly basic. There are a lot of things dissolved in human blood, including some weak bases that pull the pH up a bit. Seawater is 8.5, which is kind of equal to a solution of baking soda. Well, that would be a solution of a particular concentration of baking soda, but whatever. And then ammonia, sometimes used in cleaning. Washing soda, which is sodium carbonate instead of sodium bicarbonate. And then laundry bleach, which is hypochlorite. Anyway, these are also different common substances. And you can see they span the pH range. Again, here we've got factors of 10 for every pH unit. And then, as long as I'm on the slideshow, we'll just keep moving here. In addition to pH, which is defined as the negative log of the concentration of H3O plus, we can also define a pOH. And the pOH, sorry, let me put it up here. The pOH is the negative base 10 log of the OH minus concentration. And you can see they have this relationship. You know, if OH minus times H3O plus is equal to 10 to the negative 14th, well, what if we take the negative log of both sides of this equation? Well, the negative log of 10 to the negative 14th is 14. And because these two things are multiplied together inside the argument of the log, we can actually turn them into a sum of individual logs. like so. And in the end, we get the pOH plus the pH is equal to 14. They add up to 14. And this is going to be really convenient for us. So you see the most basic things have a pH of 10 or 11 and a pOH of 4 or 3. The most acidic things have pHs of 0 or 1 and pOHs of 14 or 13. All right. There are a couple of ways that we can measure pH. And one of them is using a universal indicator. This is a compound which changes color depending on the H3O plus concentration. And a universal indicator is a mixture of these compounds so that you get subtle color changes over a wide pH range. And it can come in the form of paper, like we see here in figure 16.5, and you'll just put a drop of your solution on this little strip of paper and it will change color to indicate the pH. It can also come in the form of an indicator that you drip into your solution, and the whole solution will change color based on the pH. And you've probably encountered indicating paper before. I can't remember if you use it in 1215 or not, but oops, we're going to skip that figure. Okay, and figure 16.6 shows another way, and that's through actually an electrochemical probe called a pH meter. You put a pH meter in a solution, and it will produce a voltage that can be measured and converted into pH with a voltmeter. And so you see that probe, you just stick it in the beaker, and the meter says the pH is 8.67. And these things are great. They respond instantaneously. You can take dozens of measurements a second if you have a good quality pH probe. And so it's a very responsive and sophisticated way to measure the pH to a high precision over a wide range of pHs and many times a second. So pH meters are pretty cool. All right, and now we have all the tools to do all sorts of conversions. When we're talking about acids and bases, one thing that we obviously might care about is the H3O plus concentration. But we might also care about the OH minus concentration. And how can we convert between these two? Well, we know that Kw is equal to their product, H3O plus times OH minus. And Kw is 10 to the negative 14th. So if I know one of these, I can find the other. Well, another thing I might care about is the pH. How do I convert from H3O plus to pH? I know that pH is equal to the negative base 10 log of the H3O plus concentration. What we haven't quite shown you yet is how to convert the other way around, and that is that H3O plus concentration is equal to 10 raised to the power of the negative pH. And that's just rearranging this equation to get rid of the base 10 log, and you end up with that. Well, you might also care about the pOH, and we can convert between pH and pOH very easily because pH plus pOH is equal to 14. And of course, we can find the pOH from the OH minus because pOH is equal to the negative base 10 log of the OH minus concentration. And we can similarly find the OH minus concentration from the pOH because OH minus is equal to 10 raised to the power of the negative pOH. And so if you know any one of these corners, you now have the tools to calculate all of the other corners. And I won't do any practice problems right now because your quiz has like a disgusting number of problems that demonstrate all of these steps. And so we'll get plenty of practice on the quiz. There's a whole, it's just like a big list of lots of little problems. So it's a bit tedious, but I don't apologize because what I really want is for these conversions to become second nature to you, things that you've practiced so well that you don't even need to think about it.